If you study the golden ratio, you'll discover Fibonacci numbers. And if you study Fibonacci numbers, you'll discover the golden ratio. Breaking news, two things in math are connected. What's the big deal? Well, these two things in particular are not just connected by some equality. They describe each other in an incredible number of different ways. Still, as rich as it is, this relationship isn't complete without the much less famous Lucas numbers. In this video, we'll explore how they tie essential golden equalities together, which sounds like a lot of algebra, and honestly it is, but with these numbers, even algebra is a visual experience. You'll see what I mean. We get the Fibonacci sequence by starting with two ones in a row and then generating each new number by adding the previous two. So it continues as 2, then adding that 2 to the previous 1 we get 3, add that to the previous 2 to get 5, and so on. Generally stated, the nth Fibonacci number is the sum of the one before it and the one before that. And the golden ratio is a number we get when defining one special way to split a line. It's a factor that describes how much bigger the bigger segment is, and also how much bigger than that the whole is. This statement tends to trip people up because it's honestly a bit of a word salad, so let's unwrap it. We'll just copy the whole and put it next to the two segments. Now we declare the smaller segment to be 1, the bigger as phi times more than 1, and the whole as phi times more than phi. We always get the next size by multiplying by phi, a number a bit over 1.5, which is the factor we are talking about, the golden ratio. Well then, this plus this equals this, right? And we can clean that up to get this. Good. Now we can observe something similar happening with the Fibonacci numbers. We take the first two as line segments to start from, and the next one as a whole they create together. So the segments add up to the thing standing next to them, just like with phi above. But the ratios between consecutive parts are not the same here. Reading from right to left, we get 2 to 1, and then 1 to 1. Making another step to include the number 3, we get another ratio, 3 to 2. And if we start comparing the ratios, we'll see that the first one is smaller than the second one, which is bigger than the third one. This pattern goes on forever. Every time we add a new whole, the ratio adjusts slightly, going up and down in succession. And these adjustments get smaller and smaller, which means that adjacent ratios keep getting closer to being the same. If we imagine doing this forever, and somewhere infinitely far down the line of Fibonacci numbers we look at 3 in a row, the adjacent ratios will be identical. And that's all that needs to happen for them to be exactly phi, because those two ratios, of parts to each other, and of the whole and the bigger part, being identical, is what defines phi. That's all that really matters. So the fact that Fibonacci numbers start with two ones doesn't really play a role. Just adding the last two numbers to create a new one does. We could have started with virtually any two numbers instead, and this convergence of ratios to phi would still happen. Negatives, fractions, irrationals, even complex numbers. It all works. Just don't put two zeros in, and you're good. So all choices of starting elements obeying this recurrence relation have this property of the ratios of adjacent elements converging to phi, but some are more special than others. The one already poking us in the eye is the definition of phi itself up here. We're starting with 1 and phi, and the next one in line is 1 and phi added together. There's nothing stopping us from going further. The special thing about this sequence is that the ratio of adjacent elements is phi, right from the start, and it will stay that way forever. Let's look closer into that. In this expression, we can rewrite everything in terms of phi to a power. 1 becomes phi to the 0th power, then we have phi to the 1st, and phi squared stays the same. The powers become indices in a sequence. And if that's true, we could multiply this whole expression, left and right side, with another phi, which would bump the powers up by 1. And we can do it again. And again. Generally, we can get phi to the nth power by adding phi's raised to the previous two powers. That means we have a sequence where elements are consecutive powers of phi that also obeys the recurrence relation of adding two previous ones to get the next one. Now let's apply this recursively. We start at phi squared expressed in terms of regular phi and 1. Then for phi cubed, which is phi squared plus phi to the first power, we can expand phi squared using the expression above and end up defining phi cubed in terms of just phi and an integer, 1. Let's keep going. For phi to the fourth power, we can use what we found for phi cubed and phi squared to get 3 phi plus 2. So some integer amount of phi and another naked integer, or if you want to be fancy, a linear combination of phi and 1. Let's do one more. And now let's line them up and fill in implicit ones and zeros, like so. Now we bring out these factors. Alright, what does this look like to you? Horizontally it's kind of a mess, but vertically the numbers add up downward. And not only that, they are actual Fibonacci numbers, starting at different points. This works because each new power just adds however many lots of phi and lots of 1 there were in the previous two. And here we can even see what comes before the first Fibonacci number, a 0 being the 0th Fibonacci number, coming in before the first and not disturbing the sequence. We'll come back to that a bit later, but for now, let's write this observation generally. Phi raised to the nth power is a combination of the nth Fibonacci number of phi's and the Fibonacci number before that. This relation is specific to Fibonacci numbers, so maybe we could use it to work out a general formula for them. Well, yes and no. What we have so far is not enough, because we have two Fibonacci terms, and only one equality connecting them to phi. But this core relationship that defines phi comes to the rescue again. It's a quadratic equation with two solutions. One of them is a half plus a half of root 5, the exact value of phi, and the other is 1/2 minus root 5 half, which also happens to be the negative reciprocal of phi. This has a lot of crazy consequences which will become apparent as we move forward. This second solution also has a name and a symbol. We assign it the Greek letter psi. And if psi is the negative reciprocal of phi, then phi is also the negative reciprocal of psi. We'll be using this a lot, so I'll write it in compact form on the side. Now, since we've derived this relationship to Fibonacci numbers from this quadratic relationship, that means the exact same relationship is valid for its second solution, psi. And that gives us the second equation we needed. We're good to go. The simplest thing to do here is to get rid of the second Fibonacci term, these guys here. We achieve that by subtracting the equations from one another. So phi to the nth minus psi to the nth equals this combination up here minus this combination down here. That lets us cancel the extra Fibonacci term, and now we can collect the factors of the nth Fibonacci number. Turn that around to isolate it, and we get this closed form expression called Binet's formula. The number in the denominator doesn't depend on n, it's something specific, which we can work out algebraically from the exact values of phi and psi, but it's better to look at this value on a number line and get a better idea about what it means. If we draw it like this, with 1/2 in the center, and remember that phi and psi are just half of root 5 away from that in either direction, that tells us this span is a whole root 5. We could simplify Binet's formula by putting root 5 in the denominator, but it's good that we know that this is what it actually represents. If it weren't for psi, this formula would just be a power function scaled down by root 5, and we could plug in any value for n, not just integers. But psi is negative, and that not only enforces integers if we want to stay in the reals, it also generates an oscillation between positive and negative values that quickly tends to 0. a convergence. When brought together in Binet's formula, we get Fibonacci numbers dancing over and under the graph of phi to the nth divided by root 5, quickly aligning themselves to it. The presence of root 5 as a scaling factor, shifting us out of a pure connection to phi, kind of sticks out for me and hints at a missing piece of this story. And that's why we need to talk about Lucas numbers. The sequence of Lucas numbers follows the same recurrence relation as the Fibonacci sequence, but their initial few elements are 2, 1, 3, 4, and so on. To compare them to Fibonacci numbers, we need to remember that these first two 1s appear if we start the sequence at index 1. But remember, we can also start them one number earlier, at 0, and that will also be at index 0. The Lucas sequence, written like this, also starts at index 0. This is important because we need to establish a relationship between these two sequences, so we have to have them correctly lined up. The link to notice here is that we can get a Lucas number at a specific index by adding Fibonacci numbers right before and right after that index. So if we take these two Fibonacci numbers, for example, and add them together, we'll get this Lucas number. And that stays true for any index n. We can write it generally, like this. So far it looks like Lucas numbers are definitely less fundamental. The choice of initial numbers feels a bit more arbitrary than the way we started Fibonacci, and we can derive them from Fibonacci numbers. Fine, I hear you. Continuing in that theme, we'll use what we've learned about Fibonacci numbers to derive a closed-form formula for the nth Lucas number. Let's just go right ahead and expand these two Fibonacci numbers using Binet's formula. Alright, these share the same denominator, so we can bring them together. And now we're going to decompose the powers, like that. And we can lose the first powers. Good. Now to deal with -1 powers, we can use the fact that phi and psi are negative reciprocals of each other. Phi to the -1 becomes negative psi and vice versa, which means we flip both the symbol and the sign. Now we can collect terms. Phi to the nth gets phi minus psi as factors, and psi to the nth does as well. And if they share a common factor, which is also present in the denominator, those will all cancel out, leaving us with just phi to the nth plus psi to the nth. Oh, this is simpler. And not only that, if we draw the same graphic of numbers in this sequence oscillating around a continuous power function and converging to it, that function will be phi to the nth, the golden ratio power function. Now the two continuous graphs are off by exactly the factor of root 5, but Fibonacci and Lucas numbers are not. They tend to be as we get further down the sequences, but at the very start this approximation breaks down. That's because of this flipped sign between the nth powers of phi and psi. If you look at the graph, the corrections happen in the opposite order. When Fibonacci numbers correct up, Lucas numbers correct down, and vice versa. I mean, okay, it's kind of visible. We can make it pop out a bit more by allowing any positive real number for n and accepting complex outputs. Here it is, first just with the real component shown. Oscillations are a lot clearer now. For the imaginary component, we'll use the z-axis, which is currently invisible because it's pointed straight at us. So let's look a bit around. It's like stretched out springs, weaving around the blue power functions. And also, if we focus on just the imaginary values, they weave in and out of real numbers, visiting them precisely at integer values of n. Both these oscillations happen in opposite order, all due to the difference in the sign before psi to the nth. This begs the question, if adding two Fibonacci numbers around an index creates a new sequence that weaves around the power function scaled up by root 5, what would happen if we took elements of the sequence of 5 powers and did the same? Phi to n plus 1 plus phi to n minus 1. We can extract the common factor of phi to the nth power, and what we're left with in brackets is phi plus phi to minus 1. This second one we can flip to a negative psi, giving us phi minus psi again, and here we go, up by a square root of 5 again. But this time the relationship is exact, which, if you think about it, should not be a surprise, because this sequence grows continuously and smoothly, always by the same factor, phi itself. But wait, shouldn't we then also be able to just add Lucas numbers around an index, and get that to weave around this new scaled-up power function? Why, yes, that's exactly what happens. And what are the numbers we get? 0, 5, 5, 10, 15, 25, exactly Fibonacci numbers times 5. We've gone up the scale by a factor of a square root of 5 twice, so by 5, and we've flipped the order in which psi introduces corrections, also twice, so we're back to an exact relationship. And because we got this result by adding Lucas numbers around an index together, we can use that to find the expression for the nth Fibonacci number in terms of Lucas numbers. Does that mean we've come full circle? Did we express every relationship in every direction? Well, not quite yet. Remember this linear combination for the nth power of phi? What if we use Lucas numbers instead? Let me guess, it's going to be something root 5, right? Let's just expand the Lucas terms using the closed form formula. It turns quite simply into this. So we distribute the phi, and look, we already have phi to n plus 1 and n minus 1 power here. This last term has a negative 1 in it. You know the drill. We change it to a negative phi. And now we can just cancel them out. And this, we already solved it. It is indeed just phi to the nth, bumped up by a factor of root 5. That's a lot of different relationships, and even if they are so intricately connected, it's not easy to keep track of all of them. So let's organize them a bit. Feel free to pause here if you need a moment to take this in. There is no specific system here. I just tried my best to arrange the equalities in a way that shows their symmetry and interconnectedness. For the basic story of these sequences and the golden ratio, this is pretty much what I wanted to talk about today, but there is a little bonus relationship I still want to show you. One that, even if you've already seen all of what I've shown you so far, you probably never encountered before. We'll start where we left off, with these two linear combinations, and we'll prepare them for being put together into a single equality. Our goal is to relate both Fibonacci and Lucas numbers to phi in the same equality. We can put these equations together, but we need to prepare them. First, we'll put this root 5 up here, and now we want to get rid of extra Fibonacci and Lucas terms, so we only have one index for each. The trick to use here is to rewrite both of these to provoke a nice cancellation. For fn-1, we can use the Fibonacci recurrence relation, we just turn it around. And for ln-1, the Lucas-Fibonacci relation, we just slide the indices down by 1. Now we have extra Fibonacci terms at n-2, but we can add the two equations together, and they will cancel out. Okay, the 1 plus root 5 on the left would be the exact value of phi if it was divided by 2. So let's make it so. We'll divide the whole equation by 2. Perfect. Now we can also divide phi out. The fn term on the right ended up with a phi to the minus 1 power, and you know what we like to do with those, right? Flip the sign, make it a psi. Now we distribute 1/2 to the Lucas and Fibonacci factors. Okay, a power of phi is a half of a Fibonacci number, plus a half of a Lucas number, and a pinch of something else. Interesting, but this isn't the most elegant form yet. We have one more step to do. We'll expand psi using its exact value, like this. And now we can cancel out these halves of the Fibonacci term. There it is, phi to a power, as a composition of its rational and irrational part, using both a Lucas and a Fibonacci number. Wait, we should draw these two components as graphs too, the Lucas part and the Fibonacci part. First, we draw the 1/2 Lucas number, and then the √5 Fibonacci number. This time they are staying together and weaving around something specific, tending towards it. What is it? It's the graph of a half of the phi power function, which means that the further we go along the sequence, the closer these two components are to exactly half of a power of phi, and closer to contributing exactly the same amount to the value of a whole power of phi. I forgot to show you where integer values of n are. Here you go. We see that these two components are always off from a half of an integer power of phi, but their offsets are exactly opposite and they cancel. You might wonder what's going on at the places where all the graphs meet, but the truth is they don't. Remember, Lucas and Fibonacci numbers are only real at integer indices, otherwise they are some complex number. In fact, these three graphs will never touch. They will just keep getting closer together in this swirly dance. Wanna see? Thank you so much for watching. I hope you enjoyed and learned something new. Please leave a comment and share your thoughts. Feelings are welcome too. Consider subscribing if you haven't already, and I'll see you again soon. Bye!